we did, more or less a presentation of the main ideas and the main motivation, and we saw some example. The example we saw was equal to minus f of x plus dw, and we saw this as an invariant measure, which is equal to minus. I have it. But talk in this way and more central. Down. This way. I don't know. Sorry? Which is it? I'm gonna get 5 minutes. Show me. No, it works. Okay. Yeah. Thank you. So you consider E f of x dx, and where we have this, and this is an invariant measure, and so we found out that also all laws are equivalent to this one, and so this is a meaningful measure, which is also a good reference measure. We can lift this problem to a d-dimensional problem without any effort, even in-dimensional. And the in-dimension is du, for instance, plus of u minus the derivative of some f of u plus space-time white noise. Okay? So, to get an invariant measure for this, we have to do 2 steps. The first step is to write down the invariant measure for the linear part. So this is the Laplace. We have some boundary condition, say a good one because I want to make simple things like Dirichlet or periodic or Neumann. And so as some eigenvalues. And so I take the Gaussian measure, which is the product of one-dimensional Gaussian with variance, the inverse of the. It's moving. The inverse of the eigenvalues, and then I take as a measure. Okay, a normalization constant, which because we want to have a probability measure, and then E minus f of u d nu du. Okay, this is a invariant measure for this system.
So, Marco, to help the student, we evaluate the mu set A as equal to the integral of this one.
Oh, okay. So simply the integral over a mu du is simply the same integral over a of normalization constant E minus f of u and integral with respect to du. So this is a probability measure because it's the product of infinitely many Gaussian. And this is a density, and that means that this measure mu, which is a product of a function and of a measure, and of the integral is okay. As we saw already in Girsanov, for instance, so this is essentially a gradient system, and the reason why we have this kind of measure is due to the fact that without noise, in principle, this should stabilize on the zeros, but also with some in the limit of small noise and small viscosity, this should stabilize on the zeros of this function. And so what we see is that the measure here is an equilibrium in which the zeros still have some importance, and then there are some fluctuations around it. Now, let's go to another approach. Because, for instance, if we take Navier-Stokes without noise, in some simple situations such as periodic or Dirichlet, so some boundary domain, so there is no energy coming from somewhere. Simply, but this is also the intuition, you move, and after a while, the fluid stabilizes, right? That means that there is only one global stationary state, which is 0. So it may make sense to approach the problem and consider the nonlinearity as a kind of perturbation. It's not meaningful from the point of view of physics, because actually the nonlinearity makes whole of the interesting thing. But if you look at a lot of the literature on Navier-Stokes, that's essentially what they do. The nonlinearity is a perturbation of the linearity. So with all the literature on mild solution for Navier-Stokes, the idea is exactly the same. You change the space, you change the norms. They really had weird ideas on how to do this, but essentially the nonlinearity is a perturbation. Okay, let's try to do this. And unfortunately, this will be the ending part of the talk. So in order to of this talk. Then tomorrow I do something else. Sorry. Okay. Before going, I need to do a bit of just to fix some definition and so on. And so I remember all the people what it is. So the idea now is we have a nonlinearity. We try to get rid of it. Okay, and so if you say we get rid of it, so in a way we linearize around the stable point. And the stable point is 0, and so linearization. Okay, so if this disappears, we end up with a problem whose laws are Gaussian, right? So the first step, we study equivalence of Gaussian measures. And this, as a secondary result of this, we see that in infinite dimension, having equivalence of measure is difficult. Okay, it's much more difficult than in finite dimension. Okay, let's start. First, I remember some things on absolute continuity. I kept talking about this, but maybe it's time to give some ideas. Okay, let's say we have two measures on some measure space, and we say that the mu is absolutely continuous if mu of some measure is 0 for every e such that mu of e is 0. So if the zero sets of the measure nu are the same, or actually are of the first measure, and then they are equivalent if mu is absolutely continuous with nu, and vice versa. And we know by okay, Radon-Nikodym theorem, I have a bit of problems remembering names, that this condition is equivalent to having a density. Okay, so the Radon-Nikodym theorem says nu is absolutely continuous with nu if and only if there is f such that nu is equal to f nu. This means that mu of A is the integral of f over the set A in the mu. So like here, mu is absolutely continuous with nu because there is a density, and mu is the product of a function and of a measure. Okay? And okay, and they are equivalent if the both are true. And in this case, the density is positive, and the opposite density is 1 over f. If I can write nu as the integral of 1 over f mu. I mean, everything works as one would expect. On the other hand, mu and nu are singular if there is A such that mu of A is 1 and nu of A is 0. So they really live in different parts of the space. And okay, this is, since we are dealing with probability measures, I take the complement of this set and I get the other side. So it's a symmetric relation, right? Okay, how to get singularity or equivalence, or what is it in the middle? Because between, say, absolutely continuous or equivalent and singular, there is a full spectrum. I mean, there is no dichotomy, either equivalent or singular, right? How to tell two measures are singular or equivalent? Well, for equivalence or absolute continuity, you try to see that the null set are the same, well, all the same. Or the null set of mu are the same of mu. Maybe mu may have more null set, but all the null set of mu have to be null set of mu. But getting the two measures are singular is tough. So the normal, the usual distances between measures, so for instance, total variation measure, total variation distance, which means mu minus nu is in total variation, is the supremum of mu a minus nu a. Okay? Okay, for this one, getting they are singular, if they are probability measures, this distance is smaller or equal than 1, and if it is 1, okay, we are in business. Or you may have other distances. For instance, you can write down this total variation in terms of test functions. So, and if you change the set of test functions, so you go from bounded continuous to Lifschitz or so on, you get different distances like Wasserstein and so on. But then it's more and more difficult to get distances. There is a special distance which has been, in a way, devised for getting singularity, but essentially for product measure, which is the Ellinger distance. But we are not going to use it in this talk. So now let's go to the Gaussian measures. Okay, so let's start with the Gaussian measures. In finite dimension. So say I have two Gaussian measures, one with mean 0 and variance sigma square, and the other one is same variance, different mean, one-dimensional. I'm going to consider the same variance or covariance in dimension larger than 1 because I'm trying to get rid of the nonlinearity. Okay, let's go back to our stochastic equation. Any one is fine. So what is a stochastic equation in the end? Is an equation that tells us the motion of the mean and the motion of the fluctuation around the mean. Okay? So we have two terms. The drift that tells us how the mean is moving, and then these are the fluctuations. And then when we have a noise which is not additive, this picture is a bit more complicated, but has a rough idea, is reasonable. Okay? So what we're going to do is we want to try to change the drift, to get rid of this part. So we are not going to change this part. And that's why now I'm focusing only on changing the mean. There are some theorems that also tell you how to change the variance. For a Gaussian measure is Feldman-Hayek, is it? Sorry? It's Feldman-Hayek theorem, right? Okay. But we're not going to, I mean, it's possible, but okay. So how do you change the mean. What I mean is these two measures are equivalent. Yes, they are equivalent because they have both positive density with respect to the Lebesgue measure, and that means that they are equivalent because I can write the common density as the ratio between the two density with respect to the Lebesgue measure. Okay, so they are equivalent. And in fact, their null set are the same of the Lebesgue measure. And if you do some computation, so this has a density which is 1 over hope I won't make a mistake. This one, so this is the density. This is actually this measure because density times Lebesgue measure, and this one is the same E minus 1 over 2 square x minus m square. You consider you divide one by the other, and this is the mutual density. And if you do some computation that I leave as an exercise, but it's really, I mean, it's almost offensive to give you this exercise. And what you see is that, and now I'm going to make it wrong. Okay, this 0 sigma square is equal to, okay, these two parts disappear because they are the same variance. So the main thing is done by the ratio between these two, and what we get is E, and then let's see if I get the right sign. Okay, I take this divided by this, and so this is minus and this is plus, hopefully. But this is always minus, actually, and this may be plus or minus depending on which one I take. Okay, and then I got this one. Okay. And that means that if I have two different Gaussian measures, they are equivalent in finite dimension. Dimension 1 is easy. If you do in finite dimension larger than 1, you get exactly the same. I won't do the computation. And we have this special term. I did this because now I want you to recognize the same term in the general case. Okay. Because now the real issue is what happens in infinite dimension. In finite dimension, what may happen? So let's say we are in 2 dimensions. So either this Gaussian measure is full, so its support is the whole R2, or maybe because when you consider in dimension larger than 1, there is a covariance operator, which is the covariance of the Gaussian measure. And if this covariance is the covariance matrix is degenerate, then we have a different story. And if the one Gaussian measure is degenerate and the other one is non-degenerate, they cannot be equivalent. I mean, but this cannot happen in our case because we kept the same variance. So if one is degenerate, the other one is degenerate as well, because it only depends on the covariance. Okay, let us see now. Let's make say a huge step and go directly to infinite dimension, because I mean, that's what I say usually. As a mathematician, we have 0, 1, infinity. The rest is more or less, maybe 2 sometimes. Okay, so since I told you I want to keep the thing as simple as possible, someone would say I'm lazy, but I will work in a Hilbert space, okay? Which is the closest thing you can consider of a Euclidean space, but with the infinite dimension. So I have a Gaussian. What is a Gaussian measure in infinite dimension? This is a Gaussian measure. If I write it and then I tell you what it is. If the image measure of mu with respect to every h in the dual space of h, so this is a continuous map from h to r. So this measure is the measure which is transported by this map from h to r. So this is a measure on r, so this has to be Gaussian for every h. Okay, this is not cyclic because we know very well what is a Gaussian measure in dimension 1. And this measure is transported from H to R. So this is a Gaussian measure on R, and we know very well what it is. And so a Gaussian measure in infinite dimension is a Gaussian is some measure which is Gaussian when projected on R in any direction of the space. Okay. If we have a Gaussian measure, we can associate two important objects. One is the mean, and the other one is the covariance matrix. And this covariance matrix is C mu of 2 HK. I'm in a Hilbert space, so sometimes I will freely identify the dual with the Hilbert space itself, right? Okay, so, and this is the integral of okay, so mean is a first order object, so x. Covariance is a second order object, in fact there is an x square. And for Gaussian measures, this is enough. This identifies completely the Gaussian measure. Okay, so which kind of simple transformation we can do on a measure in a space? Well, either we make a translation or we do a dilation, right? Or maybe a combination of the two. These are the most simple transformation you can do on the space and then on the measure. Because if we transform the space, this can be seen as a transformation on the measure, right? So now what I want to show is when this kind of transformation change the Gaussian measure in a way that become singular or non-equivalent. It may depend. Okay? Actually, the truth is, if you apply one of these transformations on a Gaussian measure, either they are equivalent or they are singular. There is no other way. Okay? Because Gaussian measures are special, and so they don't let you have weird behaviors. Now I can try a poll to get what happens for dilation and translations. So what is a dilation? What is a translation? I think a dilation has I fix C in R, and I consider the dilation from H to H defined as dc of x is equal to C times x. It's a Hilbert space, in particular is a vector space, and so I can multiply by a real number. And then a translation is I take H in H, and tau H of x is equal to x plus H. So these are transformations on the space, but by means of image measures, I can make them as a transformation of measures. So the poll is, if I apply a dilation, what happens to the measure? I get something which is equivalent, is singular. Might be that for some values it's singular, for some other values it's equivalent. For those who already know, like Chislav and 3. So what happens? Okay, you can just try. I mean, okay, no. And for translations? It's equivalent. Okay, you got 50% in a way. Because for translation, it happens that for some translations, it's fine, and for some other, it's not. And for dilation, try for dilation as well. I mean, you got 50% on the first try, so it's good.
It's also true that for some,
Sorry?
for some they're equivalent, and for some they're not.
Yeah, but for which one is equivalent? Okay, for C equal 1 is equivalent. For C equal minus 1 is equivalent as well. What else? Unfortunately, these are the only one. And for dilation, I mean, it's even worse. At least for translation, we have some are good, and but for dilation, yes. Okay. So for dilation, take any Gaussian measure, and so mu Gaussian, then mu and the image measure with respect to the dilation of mu are equivalent if and only if c squared equal to 1. It's a nice proof that I found on some notes of Martin, but I think that come from the book of Bogachev, you know, Gaussian measures and so on, which is based on the low large numbers. You find it on my notes as well, because it was too nice not to copy. And actually, I was planning to do the proof here, but I'm not managing very well the time. Okay? But I want to focus on translation, because I mean, dilation was just an idea, just to see how things go on. But translation is much more important. Why? Because still, if you remember what I wrote here, we want to take the drift and let it disappear. So in a way, we want to make a change of measure so that this drift, which is part of the mean motion, should disappear in a way, because it's a change in the mean, and also I want to see what happens when I change the mean, because a translation means I'm changing the mean, right? So the main object is translation. Okay, and there is a kind of famous, well, at least for those who do stochastic analysis, is the famous Cameron-Martin theorem. That says that if I have a Gaussian measure mu, so I identify the measure by means of the main and the covariance operator. Well, this is the covariance metric, but I can see this as a covariance operator in a standard way. So the covariance operator is defined in this way. C mu of h is the integral by x h x mu dx. So h is an element of the Hilbert space, but I can only also see it as an element. Okay, or this can be simply the scalar product in the Hilbert space. This is a number. This is an element of h. So this is an element of h. So this is the same as this one, because C mu h k scalar product is exactly C mu h k. But this is standard in Hilbert spaces. So I have a bilinear operator or an operator. Yeah, I should. You're right. Yeah, you are completely right. But okay, and now I have to guess. Yeah, x minus m. X. Okay. We'll say the. Okay. They are right, as usual. I forgot to put the dm, and as well here. Okay. With this, everything I wrote is correct. Okay, so mu is a Gaussian measure. I associate the covariance operator, and I consider this subspace of H. This subspace of H is the set of X such that this new norm, which is defined as C mu minus 1 x, and now I say something about this. Okay, then the following properties are equivalent. The first one, that mu and the translation of mu are equivalent if and only if H is an element of this particular space, which is a smaller space, because C mu is from H to H. Okay, this is invertible. When this is not really invertible, this is not the best definition. But, let's say that when it is not invertible, where the place where it is not invertible, we don't really care of it. There is a better definition than this, which is on the notes, which is independent of writing the inverse of the matrix, because indeed the theorem holds also when this is not invertible. The way I wrote is simpler, but with some problem. So, and they are equivalent if and only if this, and if this does not happen, they are actually singular. And there is a density if if any of these holds, and the density is given by this function E C mu minus 1 H x. Probably I also wrote this. Okay, minus a half H mu square. Okay, if you took notes, or if you are looking at my notes, you could see that if I compare the one-dimensional example I did at the very beginning and this one, we get exactly the same. So what we got in the simple example, we were translating from the mean from m to 0, or from 0 to m, is the same. Okay, so in the one-dimensional case, H was m, and C mu minus inverse. So C mu is the covariance. So in dimension 1 is a variance. So this is the inverse variance. So what we got in that case, we got mx over sigma square minus 1 over 2 sigma square, m square. It's the same. Okay? Is it? I didn't make any mistake. Okay. So in this case, 1 or infinite dimension is essentially the same, with one difference, that in infinite dimension, this big gives a much smaller space. Also, this smaller space is a null set for the measure, which is in a way confusing, because in a way this set tells you how the measure is done, but on the other hand is on measure 0, because and so it's a curious. Okay, so in infinite dimension we have the same thing, and so this is.
But even stronger, because it's not in some way this set tells you what the measure is, because actually the set determines the measure.
Yeah, exactly. You can write the Gaussian measure as a sum over a orthonormal basis, for instance, of this Cameron-Martin space, and so you really have this. But it's on a null set. It's a null set if and only if we are in infinite dimension. For a finite dimension, essentially this coincides with the support. Well, not essentially, it coincides with the support of the measure. Okay, that's the difference between finite and infinite dimension. In infinite dimension, this is negligible, but still important. In finite dimension is what is about for the measure.
Nice criterion for finite dimensionality of a Gilbert space.
Yeah. But I'm pretty sure there are simpler ways. Okay, so fine. But this is not what we want. Why? Because if we consider an equation, okay, let us write a very simple example. So for instance, the d of x is equal to f of x dt plus dw, and x is one dimensional. Okay? So if we look at this problem, we say we have all the assumption we need to know that this has a solution. For instance, f bounded, measurable. Even bounded is not necessary. Measurable, yeah, well, yeah, you need it. But if say f is bounded, measurable, I don't have to add anything else. Then there is a unique solution, unique weak solution. That means a unique distribution that solves this. And can you even say something more? Maybe we will. Okay. So clearly, this is not a Gaussian measure unless this f is linear. Well, the law of the solution is not a Gaussian measure unless this f is linear or constant. Constant. Sorry. Okay. And so sticking on Gaussian is not bring us very far. Okay. So we have to do something better. And this something better is what is called the Girsanov theorem. Okay?
Can you also please write down that it is the Radon-Nikodym derivative, right?
It is this one.
So if you write it down in the student's notes, it is B of...
that makes me into trouble because depending on the sign must be one. So I try one and might be the other one. So that means that TH this is equal of
just say B over D.
say of some set A is equal to the integral over A of JHX mu dx. And maybe I'm wrong, but in that case, just put a sign minus here. I have to think about, but I won't do that right now. I wrote it on the note, but might be that also in the note is wrong. But
So adding an edge, and this is how it should be. Yeah.
so it's correct. Okay, thank you. And okay, this means that this is the Radon-Nikodym density between these two. And if one of the two is, okay, if the first is correct, say if this is not true, then they are singular. So you were right. Good. And
I mean, a point we should have raised before this one, but I don't want to derail you because it's not obvious that why Lebesgue measure doesn't exist in the Hilbert space.
oh, okay.
Maybe.
Okay, I just talked about this yesterday, but in infinite dimension, getting something which is flat. Okay, the proof I know is measure the balls.
Yeah.
Okay, at least you may have some flat measure, but it's not interesting because those that are interesting are those which measure Borel sets, right? Okay, and so if something does not give some mass to Borel sets, we are not really interested. So say for Borel measure would be. The one I know looks at balls and then put them together and then some.
If you look at Poe's book on Gaussian measures and Banach spaces, the first page.
Yeah. Okay, I mean, and okay. So what we want to do is the so-called Girsanov theorem, which is in a way you can look at the Girsanov theorem as this Cameron-Martin, but more powerful. Okay. Okay. So again, what we want to do with the Girsanov theorem, we want to, in a way, get rid of part of the drift or of part of the drift. Okay. And why? Because in the end, we will use it for Navier-Stokes equation. We will take the nonlinearity and get rid of it. Well, okay, that's what we would like to do. And then we will find out that this doesn't work because the condition that this Girsanov theorem asks for to be applied, and which are essentially, we don't know how is this Girsanov theorem yet, but let us look at the Cameron-Martin theorem, which is in a way an ancestor of this Girsanov theorem. What is asked is that a difference in the mean has to be in this Cameron-Martin space, which is a smaller space. So if we want to get rid of this term, we want these to be in the Cameron-Martin space of the measure, some Gaussian measure, which is hidden because we have this term. Well, this is bounded, and then we will find out that in one dimension everything is fine. Actually, this is a very nice proof of existence and uniqueness of the law for this kind of equation. As long as we go in infinite dimension, then we run into a problem. Why we run into a problem? Because in infinite dimension, in the same space, we can have different topologies, which is in a way a part of the problem, for instance, in equations like Navier-Stokes, because something can be finite, beautiful in L2, and horrible in H1, right? So we have a different topologies, so different way to measure some objects, and this Cameron-Martin space is another way, right? So if this part we want to get rid of is not in the Cameron-Martin space, or is equivalent but is essentially the same, then we cannot do anything. Okay, and that's why. So we will realize that even in 2 dimensions, we cannot use Girsanov theorem to get rid of the linearity of Navier-Stokes. Okay, actually for 2 dimensions we are almost there. The 2-dimensional case is really borderline. You see that you try hard, and well, we didn't. I mean, there was some people tried, like Da Prato, Debush, Mattingly. You knew already about this name because they were already done. They tried hard, and they went almost there. So this is a parameter, and if the parameter is some value, it's fine. But for the equation, we get that the parameter is exactly smaller than that value. Smaller or equal would be fine, but it's smaller. So even in 2 dimensions, that doesn't work. So we were going to develop all this Girsanov theorem, make a lot of efforts, and then we will find out that it's useless. Unless, okay, and once you are in the bottom, we try to go up, unless we consider finite dimensional approximations. Finite dimensional projections. Once we do this, and this is a key point, once we do this, we solve the problem of topologies. Because in finite dimension, all topologies are the same. H1, L2, for a finite dimensional object, there's a constant, okay, but this constant is anyway, is fine. So as long as we consider finite dimensional projections, we overcome the problem of topologies, and so we overcome the problem of this Cameron-Martin space. As long as we have some invertibility, and we will. It will be our main assumption, actually. Okay, and the only assumption, in a way. As long as we have some kind of invertibility of the covariance of the noise, we will be able to use it, because we will solve the problem of topologies, and so no problem for this Cameron-Martin space. Okay, let's go to the Girsanov theorem. So now you have an idea on what I'm going to do. So try to push up to the end this Girsanov theorem method for SPD, and we will realize that more or less none of the interesting SPD would make the Girsanov theorem work. So my personal advice is, if you have your SPD, don't try it. I mean, it's almost useless. You won't have a good condition. Because if you have those good conditions, you can do it much simpler in a different way. Well, sometimes it works. And that's exactly what I'm going to show. And in the proof, which at this point we will do tomorrow, in the proof you will see that this finite dimensional thing will come into the game twice. One for these topologies, and then a second time, which is a bit hidden, but you will see, hopefully, that it will work. Okay, so what is Girsanov? Okay, let's make an example. Okay, so let's start with the linear process. 1 dimension, infinite dimension, doesn't matter. Let's say 1 dimension, so I don't have a problem. So that means this is a standard Brownian motion. And I consider another process, an adapted process. And let us consider this function, g, Let me write it. Let me copy it so that I put the right sign. Okay, and so let us see what we can say about this function. We apply Ito formula. Now we are extremely expert in the Ito formula because it's days we see about that. So you can even do it while I'm cleaning the blackboard. Okay, so this new process, this new thing is a process. So I apply, and this is a function of this. I apply Ito formula on this. I notice first that g of 0 is equal to 1. Now apply Ito formula on this. So what happens? I have something which depends on time, so I take the derivative of this. I get minus 1/2 xs squared. And see, this is an exponential of something. I still have this one times, okay, the derivative in time, which is minus 1/2 xs squared. And I have the martingale part. Then the Ito correction. What is the Ito correction? Is 1/2 times xs squared. That means that this is xs t. Sorry. Thank you. xs xt gt dw. Okay. So the Ito differential of g is this one, so we can write this gt as 1 plus integral from 0 to t xs gs dws. And so this g is a local martingale. Okay? And well, it's a local martingale because we don't know if this is a martingale. This is a usual problem when you deal with even with the stochastic equation. You try Ito formula, and unless you know that you can manage to show that these are quadratic variations, and so on, this is just a local martingale. And this is a major problem because we will see that if this is a martingale, this is essentially the main assumption of our Girsanov theorem. Okay? And we will see some condition that ensure that, given starting from this process, that ensure that this is a martingale. And why being a martingale is important? Well, first thing is if G is a martingale, the expectation of GT is equal to the expectation at any other time. So this is 1. And now we will see why we like this. I think that this is even equivalent. For a local martingale, having the expectation might be. Okay, so let's see the Girsanov theorem. So, if this G is a martingale, if you set Wt tilde equal to Wt minus integral from 0 to t xs ds, then for every t larger than 0, the process Wt tilde is okay, so we started, let me remember. We start with the Brownian motion, and we will do an easy generalization to any dimension. We start with the Brownian motion, or linear process in general. We consider a perturbation. We define this function this function, this process, for our assumption, turns out to be a martingale. And this is a martingale. This new process is, again, a linear process. But not on the original probability space, but on a new probability space, which is essentially the same, but for the probability. So with respect to the probability, so gt times p. Okay, let me see. I start with the idea. I'm very sloppy. I should have said it. So I start with a process on some probability space. Okay, so some probability space omega with some probability p. This space is large enough I can consider a linear process on it. I add a perturbation. I do some computation on the perturbation. And if I define this new process, so look at this process, is our same linear process, and I change dynamically the mean. So what means that when I will go to this, I will make it disappear. We will see this. Okay, I change dynamically the mean, and I get the same thing, but on a different probability space. With this probability, is it this a probability? Yes, because the expectation of gt is equal to 1 for every t, and so the total mass of this measure is 1. And so it's a probability. That is the key point, why we need, well, one of the reasons we need that this is a martingale. Okay. Now let's see what happens in our problem. So I have my problem dx. I have my problem dx equal to f of x dt plus dw. And now what I do this. This is equal to dwt plus integral from 0 to t of f of x ds. Okay? Nothing has changed. If I compute the differential of this is dw. If I compute the differential of this is an integral over boundary variation function. So the differential of this is exactly fx dt. So nothing has changed. It is kind of thing that mathematician likes a lot. You take something, you write it exactly the same, but in a very completely different way. And it turns out that this is a very smart way to do things. So what is the smart way? I change the probability. Unfortunately, here I have a minus, but if I have a plus, so what I do? I consider this as my new process, w tilde. And so I find a new probability space in which this thing is a linear process. Or vice versa, because then I find that if the situation is good enough, for instance, it depends on some information on f. For instance, bounded is very good information, that this density is positive, and so I can invert the density. And so what I say is that I can go back. I start with the linear process, I apply the inverse density, and I end up with a solution of the equation. Okay? And that means that I can characterize the law of the solution to this equation by means of a density, which is, well, can be considered known, and of the law of a Gaussian random variable. And so that means I know how is the law of this process. And how I do this, I simply take this drift part as part of the noise. I can do this, but only changing the probability space. But it doesn't matter, because if you remember, okay, this is a very loose connection, but if you remember when yesterday we were talking about weak solution, I insisted on the fact that weak solution means we're interested in the distribution, as well as here. Here, this is a stochastic equation, and for stochastic equation we have two different kinds of solution: weak solution and strong solution. This is only weak and strong in probability. Here there is no PDE, so there is no doubt that is weak and strong for probability. Weak means that we identify the distribution. Strong means that we identify the process. Here, we do not identify the process because we are changing the probability space. So there's no hope. So we are really identifying the distribution. Okay. So how the Cameron-Martin space enters into the game? Well, here we are dealing with a one-dimensional problem. And for one dimension, usually, everything is easy. But if you have a covariance here, in order to do this and get the same, the covariance should be here. And so here you have an inverse covariance. That's a problem, because now you want this to be a martingale. We haven't seen yet which are the conditions to have a martingale. But if you have an inverse covariance here, this is not going to be a good thing. Because now you claim that this drift has to be an element of the Cameron-Martin space. Because as in the case of Cameron-Martin, you allow for some change in the drift, but only if this change is in the Cameron-Martin space. So these are only the good direction to change. You just imagine, you are in an infinite dimensional space, and you have infinite direction to move, and the only direction which you can move and keep a measure which is equivalent are only those given by the Cameron-Martin space. And if you do this for an equation, then you really need that in some way, at any time, you are moving along a Cameron-Martin direction. Okay? So, typical condition to get that G is a martingale is the so-called numerical condition. That means that says that the expectation of the exponential of a half integral from 0 to t xs squared in ds, this is finite. Now this condition tells us that we are going to fail for Navier-Stokes. Why? Because we go back, we remember that we want to get rid of the drift, and the part of the drift we want to get rid is the nonlinearity. Nonlinearity is quadratic. If the nonlinearity is quadratic, if I take another square, I get something which is exponential or something to the fourth power. And we know that it's not going to work. Because for a Gaussian measure, I can at most integrate an exponential square. By exponential 4, there's no hope. Okay? Okay, this is not the real part of the problem. And in fact, now we see that this can be avoided. What time is it? It's 5 and 5:30, right? Okay. I had 4 pages and 1.5, but that's fine. Okay. So I will skip the part in which we show how to prove existence uniqueness for this part, for this thing, but the idea is essentially the same. For existence, you start from a linear process, you define a new probability by means of this density, and in this new probability, your process is a solution to the equation. Fine. And if you have 2 different ones, you change the probability and you get the same. But so if you go back, you have to get the same as well. It's not very good proof, but the idea is that essentially this thing is characterized by the distribution of linear process, which is given, and by the density, this time written on the starting process. Because when we go back, this time we started by this. Look, we started by W, and we defined this as this one. We can go in the other direction. What I mean by other direction. You start by dW, and you write this as d of dt minus integral from 0 t f of dw s ds plus integral plus f of wt dt. Okay? So that's the other direction. So I have a dw, I write it as dw minus this part plus this part. Now, this time, I want this to be, again, a linear process. So I change the probability, I define the density, but the density is given in terms of this process. So you have an explicit representation of the density in terms of the starting Brownian motion. I change the probability, and in this new probability, the original process is equal to f of itself plus something which is, in the new probability, a linear process. So I define this w tilde equal to w minus 0t f ws ds. And then that means that dw is equal to dw tilde plus f of w. Okay, dt. Okay. Now, under the probability, under the original probability, this is meaningless because I started with w, which is a linear process, and this w tilde is something else. We don't know the distribution. Well, we can compute it because we know how it is, but not really useful. And I have this thing. But now, I go in the new probability space. In the new probability space, this w tilde is a Brownian motion. And so when I look at this equation, this is exactly this one with x replaced by w. And now, this time, under this probability, w is a solution to the equation. And so I can write this distribution in terms of the density with respect to w, which is the one I started with, and with the density, which is exactly the one given here. So this characterizes completely the law of the process, up to some time t. Unfortunately, all this works for a finite horizon. If you go to time infinity, this does not work at all. Okay? And there are several reasons for why this is not working, and because I don't know a good intuitive reason. But let us see. Let me see. Let us see a very easy argument that shows that. Maybe we don't see it because. Maybe you don't see it because I cannot do it. Oh yeah, no, we see it. Okay, it does not work with t equal infinity. Okay, in terms of existence, uniqueness, this is fine because for any time interval, I know how is the law. I know that any two laws should coincide, and then if I take any chunk of time, and then the processes are equal. But if I ask that for instance, this one, this and this are the same, are equivalent when t is equal to infinity, so we can imagine in the density we have t equal infinity, this does not work. Okay, let us see a very simple example in the same setting we saw. Just take the process xt we are transforming to be a constant. Okay, constant. And so what we get is, the equation is, okay, no, wait. This x is different from the other x. This, so let's say we are doing a transformation for this equation. Dx is equal to c dt plus dw. Okay? So what is this? The law of xt. The law of xt is Gaussian of variance 1 and mean. Sorry? Yeah. And is city? Yeah, city. Okay, let's say city. Okay? So by the law of large number, I know that the limit of xt over t is equal to c with probability 1. Okay? But if I change the measure, under the new measure, and now I have to consider the infinite. Because if I do a limit at infinity, I need to look at the whole trajectory. Okay? So the event of the law of large number is an event that works on the whole time horizon. I just cannot look only at a finite chunk. I have to look at the whole trajectory. Okay? So I really need to do a transformation with t equal to infinity. Let's say we can do it. Under the new probability space, what I do, I just get rid of this. And so under the new probability space, this one is again a Gaussian measure, but with mean 0. And so this limit is 0. So with probability 1. So as long as this constant is different from 0, I've seen that I have found an event which is of probability 1 for one measure and probability 0 for the other measure. The event is essentially, it is 1, because as long as this is 0, it cannot be C with probability 1. So I'm thinking at this event. So P of E is equal to 1. G infinity of P of E is equal to 0. That means they are singular measures. So there is no hope to go up to infinity. Okay? So this is a limitation of the methods, but it doesn't matter. For our purposes, this is no problem, will not be raised. But keep in mind that you cannot do at time infinity. Now, we still have one task, which is try to figure out how to solve this problem. Because if we go with Navier-Stokes, even though we project in finite dimension, we still have a square. And if we square again, we have a fourth power. And if we weigh the e to the power 4, no Gaussian measure will integrate e to the something to the power 4. Okay? So regardless of a finite, infinite dimension, doesn't matter. This is going to be a problem. So what we need to do is to try to figure out how to solve this problem. Okay. And the idea is we need to get something which is weaker than this condition. And as usual, there is a trade-off, you know? You make something simpler, you're going to pay somewhere else. Okay? But we will see that the price we will pay is something that we will say happy to pay. So paying is not never happy, but okay. And this idea is a theorem that I learned from the book of Lipster and Sheriaev. Okay. Don't look at the way I wrote. If you really want to look at the book, just go in the notes and there is a correct reference. And because I'm not sure I wrote any of the name in the correct way. But if you look at the references, it's correct. Because I cut and paste from AMS. So Matzanet. Okay, and this theorem says, okay, so which is our idea? We have an equation, dx equal to f of x dt plus dw, and we changed the linear process in such a way that it became another equation. The equation was dx equal to dw, right? So in principle, we can do the same with different drift. Okay, so that's what we do. So let us consider two different equations. with some covariance, which has to be the same. I usually got a half, and so I take a half. Okay. Say same initial condition, and I take it also 0, just to get rid of problems. Okay. Oh, one of these can be 0. Sorry, can be 0, no problem. But I kept both just because the condition is not as one would like on the difference between the two drift, but on each drift. That's why I kept both. Okay, we need some assumption. First one is the price we pay. The price we pay is that both equations have a unique, strong solution. So you shouldn't hope to use this theorem to prove existence or uniqueness of your problem. Doesn't work. As an entry fee, you need to have both problems with a unique solution, a strong unique solution. That means that you can really give the process, and you can find, starting from that process, something which is solution of the equation, and is in a way function of this process. Okay, we will see tomorrow a bit better how this works. So, first requirement is this one. The second requirement is essentially some weak version of the Novikov condition. Let's look at the Novikov condition. This is the expectation of exponential of this term. When we know that this is a positive, we know that this is finite. That means, in particular, we know that this thing is finite with the probability 1. Okay. And since this is exponential, if this is finite with probability 1, also the exponent is finite with probability 1. Okay? Okay, and then we see that this is exactly the condition we need. The condition we need is that the probability of, okay, here I want to do it in finite but larger than 1 dimension, because now I'm going to apply this theorem in the last part, in the tomorrow part of the talk. Okay, so I state it with in finite but arbitrary dimension, because then I want to use it. Okay, so here I stick on the 1 dimension because it's simpler, but now we need a larger dimension, but it's not dramatic. So what we need is yeah, okay. The psi and eta are belong to some RD with some D, and so these are vectors. So I can take transpose. So C, this is the C minus 1 B psi ds. This is finite with probability 1. Okay, this is the matrix stuff, but let's look at this thing. Say the covariance is the identity, so this means the norm squared of V, right? So this is not any different from what we did here. So this B is a vector, C is a symmetric positive matrix because it's a covariance, and so this B, C minus 1 B, C minus 1 is also symmetric positive. This is a quadratic form. Okay? And if C is identity, this is exactly B squared. So nothing different than what we started for. And this condition has to hold also for the other one. Sorry. Psi C minus 1 B psi ds is more than infinity, equal to 1. And condition 3, same as 2, but with eta. Okay, let us see. We have two processes. The one is solution to the first equation. The other one is solution to the second equation. And my condition is a bit on the one hand, is much weaker because I don't require that the expectation of the exponential is finite. And we know that it is not going to work in our case. I require something which is less. So if in the end we use the nonlinearity of Navier-Stokes, we ask that, so this is something square. We only ask that some integral or some fourth power of the solution is finite, which can be possible. It depends on the topology. Or if we are in finite dimension, it doesn't matter, and if you have some fourth moment of the solution, we are in business, and we do, because even in 3 dimensions, we know that the solution has any moment in L2. Probably you've seen this in some previous lecture. And so this tells us that really we can do something. Okay, but let's see. I told you that we make this condition weaker, but we pay some price. The first price we pay is we need that these both have a unique strong solution. The second price is that the condition does not involve the difference between the two drifts, which would be natural if you play the same game I played here. You add and subtract the same thing, and you get something which, in a way, the perturbation is the difference between the two drifts. No, it doesn't work in this way. You need that both solutions in both drifts need to be finite with probability 1. So much less than what is needed, but still something. If one of the two drifts is 0, we only have one condition, but on both solutions. So if, say, this one is 0, this disappears, and the corresponding one disappears here, and we're okay. So let's keep in mind this, because tomorrow we are going to use it. Okay? We are going to use it in our first proof of existence of densities for the projections on Navier-Stokes. So in the end, after only 3 hours of the 6 available, we will see something about Navier-Stokes. Okay, so I still have 10 minutes. And okay, we still have some stuff to do, so no problem. I did the Girsanov theorem in finite dimension. Clearly, there is an infinite dimensional version, and this infinite dimensional version requires that we know that we can get rid of the part of the drift which is in some Cameron-Martin space. Let us see which Cameron-Martin space we need. Oh, you're right. Okay, so if 1, 2, 3, then the laws of psi and eta are equivalent on every finite interval. So I start with 2 different stochastic equations, different drift, same fluctuations. I have these conditions, and then the law of these and the law of these are equivalent on the whole, in the sense of path. So in a way, much stronger than I was claiming at the beginning. Because yesterday I told you that the main aim was to show that for a fixed time, I want to show that some random variable, which is the process at that time, has a density. Now we are doing something much stronger, because we prove that equivalence at the level of the whole path, okay, which is stronger, but requires much more. So they are equivalent on some 0t, and we also have a density, and the density is exponential of 0t of b minus b transpose c minus 1. Well, now you can see, you can write in from, you go from the law of psi to the law of eta, or vice versa. Let's go from the law of psi to the law of eta, and so I integrate in eta. This is not the same eta, it's just the variable. And it's same old thing. here we have minus half the square of the drift, and here we have the drift. Oh, no. The square of the drift times the process. And for the density depends on the difference between the two drifts. Although this is not true for the assumption. The natural assumption would be that only this difference satisfies this way, but it doesn't work. We really need, for the whole thing to work, for this assumption. Okay, and the essential reason is that you work on, you localize with stopping times. You have to ensure that these stopping times are finite and they capture the right thing. So you need a unique solution. If you don't do this is not true.
I have a question.
Sure.
So this is in Lipson and Scheyer, right?
Yeah.
So, but look at the book, little book, Studies in Stochastic Processes by Skorokhov.
I don't know. I mean, I never.
He also has a theorem like that. I was wondering whether this is the condition he puts it.
Well, okay. When I'm once, okay.
Right, a little book.
No, I don't know it. But when I presented this I presented this in a few months ago. There were some people that were very, very mean, and they don't let you pass any error. And I didn't actually, to be honest, I didn't realize that this assumption is essential. And they point me out that without that assumption, you may end up proving something which is wrong. Okay, so I don't know the book we are talking about, and they might have something similar, but I'm pretty sure that this is an essential assumption. Because there was Francesco Russo, some of you may know, said, if this is true, I'm going to prove the hell of a theorem, because it's. And then he thought about this, and then he realizes that you really need this assumption. And now I'm telling you this assumption, but all the kudos are to Francesco. Okay, so this is the conclusion. Now let's see the infinite-dimensional version, which is not really exciting because now we know how it works. So the infinite-dimensional version, and so infinite-dimensional version. So we have a covariance operator C, and psi, a function from 0 infinity with values in the Cameron-Martin space, essentially, of the Gaussian measure that generates the linear process we are dealing with. So here we have a covariance. I'm thinking at the Gaussian measure 0C. Why? Because if I consider this process, WT, this is the C-linear process I consider in the equation, I will do. And if I consider the law of this process at t, say at time 1, the law of this random variable is exactly this one. Okay? And so this is when I say the underlying Gaussian measure that I have in mind is this one, even though I have a process, but this is a linear process. So, okay? So now consider a function which is Cameron-Martin space valued, and this is an essential, and we know why this is true. And then if we consider W tilde equal to Wt minus integral from 0 to t C minus a half psi S in ds. So psi can be a process, and we consider the inverse of C here. It is fine because this map is valued in C half of C, so this makes perfectly sense. And so this is a linear process with respect to the probability GTP, where the density is what you hopefully now you expect. E to the 0t C minus 1 psi dw minus a half C minus a half psi square integral 0t in ds. Okay, it's the same as usual. So, just to summarize what we have done today. We have studied how to change, in a way, the mean of a Gaussian measure first. And then we say, okay, this is only the first step, but we want to do this at the level of stochastic equations. Stochastic equations do not have a Gaussian law unless there is a special case, such as constant drift. But in the general case, we have realized that we can still change, in a way, dynamically the mean of the solution to the equation by absorbing part or whole of the drift in the fluctuations. In order to do this, we need to change the probability space. Okay? But this is fine, because even though we change the probability space, we change it with an equivalent measure. So if we prove that at some level, some equivalence with a measure, this equivalence is kept. Because from the probability P, I pass to the probability GTP. Now, if I have that some measure is absolutely continuous with respect to this one, this will be absolutely continuous also with respect to the original probability. So we don't lose anything, at least in terms of equivalence or absolutely continuity. But that's fine, because that's our aim. Okay? So in this way, we can reduce the problem. Problem is, this is not useful, at least in a straightforward way. As I said, even in a simple case like 2D Navier-Stokes, this does not work. Maybe we see this tomorrow afternoon. Because now, I have 2 minutes, but would be pointless to start now. So I stop. Thank you. But we still have 2 minutes for questions. Oh, no. You can do it also with motivative noise. But it's a bit more difficult, because you have to be, say, for instance, here. Well, yeah, okay. But if you have, say, you have an equation like this, the x equal to f of x dt plus sigma of x dw. So what you would like to do is, say, I want just get rid of this, is sigma x d of w plus integral from 0 to t of sigma x minus 1 f of x. Yes. Okay? So just to make it simple, I mean, so now you have to be sure that this thing is meaningful. And so this f has to be in the domain of the inverse of this operator, or this function if one dimension, but let's think at finite but larger than 1 dimension or infinite dimension. This is an operator or a matrix in some RD. So you have to be sure that this is makes sense. And the whole thing makes sense in terms of being in the Kalman-Martin space. So you take the norm square, you use your Novikov condition, and you have to get something finite. For instance, if sigma is bounded away from 0, okay. If sigma is bounded away from 0 from infinity, that's pretty much. But this is essentially the additive case. I mean, it's not that different. I mean, you know. Or you have a very good problem in which this works. But if you don't have a very good problem in which this does not work, well, you may go from a less direct way, which means you go through Maillard calculus. So unless this is work, I mean, and even with Maillard calculus, but with Maillard calculus you can consider.
About regularity concerns about the existence of the inverse of the Maillard
Yeah, exactly. Yeah, this is is a first order condition. Yeah, and the Malevin derivative is a higher order condition. This is you just what you do here, you just invert the covariance on the drift, and it might not be the best thing to do. And so with Malevin calculus, you in a way you invert a bit, and then you use the fact that you have a process, so you can do this at different times. This is not what Malevin did it, but that's a heuristic idea.
Maybe to help a student, students, maybe one can even comment that in finance, you start with a semi-martingale model, right? And then
Yeah, this is
so if you can find
the neutral market, yeah.
Change a measure to make it a martingale, and if that change it gives you a unique transformation, then you have a option price that is unique also.
Yeah.
So that's at the heart of option pricing. This Girsanov transform.
Because in a way you go in a market which is what do they say, neutral? I don't remember.
Yeah, risk neutral.
Yeah, risk neutral. Yeah, right.
So that this theorem gives you a way of calculating the price.
Yeah.
So it's at the heart of financial modeling.
Okay. Then thank you. See you tomorrow.